Hi everyone, so the next videos that I'm going to be doing this afternoon are looking at the asynchronous I/O communications stuff that's going to become important for the project. Before I go into detail about how the libraries work and before I just say, yep, this is how it works, blah, 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 I sort of want to give a bit of context to it as well as how this, or using this sort of functionality relates to embedded systems in like a normal sense. So I don't know if I really covered this in the initial lectures because it's quite a while ago now. I can't remember what exactly I did. But one thing that we're not going to be directly confronted with this semester, given that we're not using embedded systems, actual boards, is that we're not really going to be confronted with hardware interrupts. Now, to try and emulate similarity, like to emulate the functionality, there are things you can do. There's software interrupts, which is exactly what we're going to be sort of making advantage of in this project. But this I wanted to sort of talk about what they are before I talk about software interrupts, because we're going to try and get everything we're doing this semester, we're going to try and do it in the context of embedded systems, so that when you are confronted in the future with actual embedded systems, you should have a bit of an idea. So I found this really nice page from Tutorials Point that I think does a very good job of explaining it. It's not too low level like Wikipedia tends to do sometimes. So if you want to read this is the page it's called, but I'm going to go through a very brief explanation of what it is. Now, so an interrupt in a hardware level. So now I'm going to talk purely about hardware interrupts. So a hardware interrupt, like when I was talking about the tick of, or how hopefully you found out when I asked you this question in exercises, the tick on a embedded system running like FreeRTOS, like the sys is generated from a hardware timer. And so a hardware timer is a peripheral part of the microcontroller, like the actual processor, that can be configured to count to a certain number separate from the CPU. So the CPU doesn't actually have to increment the value. This hardware timer just sort of sits there, ticks away, and then when it reaches some value, it sends a interrupt signal. And so interrupt signal is a hardware signal that goes to the CPU and actually says, hey, this has happened. Like there's an interrupt line, and it's a signal that actually interrupts the CPU. So like the name is very apt. So how we handle these interrupts is when you get into sort of like where the other peripheral, the NVIC is. So it's the thing that stands for Nested Vector Interrupt Controller. And as you can imagine, you have like the timer, you'll have DMA, you'll have peripherals, communication peripherals like SPI, I2C, UART, Ethernet, and all of these things can send different interrupts. So you need to have a way of handling all of these different interrupts so that they're not all just spamming your CPU and you actually know what has interrupted. Not that there was an interrupt, but better said, this peripheral has interrupted us at the moment. So why interrupts are really good is because you have, like, for instance, when we're talking about like pressing a button on a microcontroller. Now you can write a task to check your buttons that runs every like 5 milliseconds and checks, hey, it'll like send the check GPIO pin, is the GPIO pin low? Like, has the button been pressed? No. Okay, continue on, all good. 5 milliseconds later, checks again, is it been pressed? Low. Now every 5 milliseconds doing this check, this is running code on the CPU. This is taking CPU cycles, and it's really, if no button's been pressed, nothing's happened, there's nothing to do. So the running of the code is wasted CPU cycles. Now interrupt, on the other hand, when a button is pressed, you can configure the interrupt to be fired when this GPIO pin changes its state. So there's all different configurations, rising edge, falling edge, high, low, what have you. But essentially, the basic idea is that when you press this GPIO button, when it changes its state, it'll trigger on a hardware level an interrupt that will send an interrupt signal to the NVIC, essentially through like the manager of these signals, which will interrupt your CPU and say, hey, this GPIO button has just triggered an interrupt, and then you can go and you can handle the pressing of the button. But the advantage is that you haven't been running this checking code every 5 milliseconds. If the button hasn't been pressed, you don't do anything, you don't waste CPU cycles. So there are obviously advantages of both of them, blah, blah, blah. Like interrupts are also not always ideal, but this is probably a bit beyond the scope of this course. But this is the basic idea, is that you're having polling, which means you're overhead, you're checking, or you have interrupts. Now in the emulator at the moment, we're sort of using a polling way of getting the buttons pressed. You say, get button or update buttons, whatever it was, and you get from the TUM events library, you're getting the new button presses. And so this is polling. But what the library that I've written for the comms does, it works on a sort of a pseudo interrupt basis, because you have software interrupts which work the same way, but they're implemented on a software level and not obviously on a hardware level. But this is beyond, I'll get to this in a minute. So but how on an embedded system, this NVIC, or how the interrupts are actually handled, meaning like, hey, this was a GPIO interrupt, this was a UART interrupt, blah, blah, blah. This happens through, I'll get to this in a second, this happens through a vector table. And so if your vector table is something where, I wonder if I can find an example actually really quickly. Maybe. Let's just have a look in here. Did it make a map file? Yes. Yes, here we go. So this output map file is a mapping of the memory. And so in here somewhere should be the vector table. So we'll have like reset, text reset handler. Nope. Default handler. So here this looks like, you'll see here these IRQ handlers. So this is interrupt request handler. I can't remember what the IRQ stands for, but these here, this is a table that has a list of all the different functions that handle certain interrupts when they happened. But in a very basic and more human readable form here, you have, for instance, the interrupt that you have, like you have a serial communications, timer 1, external hardware interrupt, this is probably some sort of GPIO pin. And then you have this sort of vector table, which is stored in your ROM, which says, hey, when, if this is interrupt 0, it will go to the memory location 23, and in there will be a pointer to the memory location that stores the handler. Now, the handler itself is a function that you write with a specific name that when you compile and link your program, the function's address ends up in this memory location so that your interrupt handler jumps to it. So you can write a function that handles the interrupt when it comes in, right? And so that is what this interrupt service routine is. IRQ, man, okay. And so the ISR is a function that you write that then gets called when the interrupt gets invoked, or when the signal arrives at the NVIC or your CPU, right? And so when you're executing with your code, like so your main, this will be your program that your CPU is running, like your microcontroller is running, and then there'll be some sort of an interrupt will come in and it will jump into this ISR. And this works in a way, I think it's detailed here. It works in the same way as when I was explaining how FreeRTOS can change context, can run different tasks. It works in pretty much the same idea in that you sort of save the context of the current code. You can think of it like two tasks. An interrupt is one task and your main code is another task. And it goes in and then it loads, it'll go to the register. It'll get the address of the ISR from the interrupt vector table and it will jump to it. So it'll go into your ISR, like this is the handler. And it'll execute this, the routine, and then it will return from it and it'll essentially jump back into your normal program execution. So it's slightly different on like a very low level basis, but you can think of it, it's very comparable to using this context switching, which we're talking about in a FreeRTOS sense, like in a scheduler context. So that's what an interrupt is. It's a hardware signal that comes in and it will jump your CPU's code execution to a specific function, which is determined based on the interrupt number and then the function itself, which you can write based off of this lookup, this vector table, where the function has to be explicitly named with a correct name for it to be executed from this table, right? So how I've decided to sort of give some sort of a similar exposure to this is using Unix Linux signals. Now these are software interrupts that are implemented in the kernel. So in the Linux kernel, being on a software level, like the Linux kernel obviously has hardware interrupts that it deals with from network cards and all the different types of peripherals, but that would be a whole different bag of worms if we were to go into looking at hardware interrupts in this course on a Linux system. but we can use software interrupts. Now these are very common. I think a lot of you would have probably seen, like when you have a segmentation fault, there'll be like sig sev or something come up on your screen, you know, or sig seg or something, I can't remember what it's called. Now what this means is that your process was delivered a software interrupt with this signal. That's probably written right here somewhere. But here are some of the common ones. There's a heap of them. So sig, seg, that one. This will be the one saying that the kernel has said that you have a memory error and it sent this signal to your process to kill it, to interrupt it because of this error. And so this is how signals work. They're essentially interrupts handled by the kernel themselves. And so we can make use of this in our programs, which are happening in a purely software sort of like world, right? And so I think I'll get back into that when I look at the library. But now I just wanted to look at some code. I just Googled in some quick example code and found this site. So it was Panda Fruits, STM kind of UI example. But I just wanted to sort of, this is written for an STM32, which is the board that we would have used in the lab. And I want to sort of just quickly go through and explain like how you would set up a interrupt on an actual hardware platform. And then how it's instrumented, right? So in here we have this UART, like we're looking at a UART interrupt, meaning this is the communications. And so this interrupt is probably going to be called when a packet is received or sent. Usually a UART interrupt makes sense when it's received, right? And so you can see here you have this UART init structure, and this is how you initialize the peripheral on an embedded system. I think here, like this is the init type, and this is sort of how the UART or the STM32's peripheral libraries initialize their structures. The peripherals, you create the structure, you populate it with all the different options, and then you call an init function like here. Now, so this is what we don't really interested in this. What we are interested in is this guy here. So it's enabling the interrupt. So this is the NVIC. So this is the nested vector interrupt controller. And we're enabling the interrupt for USART1 IRQN. Now, if we look at this function call in some more documentation, it enables the device-specific interrupt. Now, the IRQN, this one parameter passed into it, is the interrupt number. So the interrupt number, as this guy was showing you here, for instance, this table has like, this is signal number. Oops. Like this table here would be, for instance, like 1, 2, 3, 4, 5, right? Like the actual names of them are just macros and to make it human readable. But at the end of the day, these are all just numbers. And so the number passed in here, this is this USART1 IRQN. And so the number that it actually represents will be defined by, this example doesn't have all of the includes in it, it's probably in here somewhere. Because if we look at this, it's a device-specific interrupt number. And if we go in and look at the vector table, where was I looking before? Why did I have this page open? Here we go. So this IRQN type, so there's a definition of the IRQ numbers, and they're defined in device header files. And so the device header files are essentially specific to a certain board. And so like an STM32F429 microcontroller will have all of these definitions released by ARM or by STM that sort of say, yep, UART1 interrupt is the vector or the interrupt line 10. And so this is when you have device-specific definitions that actually enable you to use these generic high-level libraries. But so we've registered this NVIC, and now if we're looking at like a good example was when I've already closed it, was that you have some function that needs to get called for like when this interrupt happens, this service routine. And so you need to create essentially this function that has this exact name. And so these are given, for instance, like here, you'll see all of these different names, SysTick, IRQs, whatever, and there'll be a long, like sometimes, I'm not sure where you'll find them on this website, long lists of all of the different IRQ names. No. But what you have to do is you have to implement that function, and then in this example, like they've implemented this function, whenever the UART interrupt is fired, when like a packet comes in over the UART peripheral, this function will get called. And so here it's checking that the UART is checking the interrupt's status. So it's checking that it's not reset. So it's actually checking, yep, this is the correct interrupt. So it's sort of like a sanity check. And then it will receive the data, because the interrupt's not actually receiving the data. It's just saying, hey, there is data in the peripherals buffer, and then you can actually receive it and then do whatever you want. So in this case, it's checking if there was a T transmitted, and if there is a T transmitted, it toggles this LED toggle function here, which just does this stuff by toggling an LED button, right? Bit, GPIO pin. So in this case, we have no polling, and when we send a T to UART, it'll interrupt the CPU and run this function, and if a T is there, it'll trigger the toggling of the LED with minimal, so obviously this is getting run on the CPU. I mean, this is in an interrupt context, like once the swaps happen, but the CPU doesn't have to constantly check if there is data waiting in the UART peripherals buffer, right? So Linux works in the very same way, but you don't have to configure peripherals or anything, but you definitely, there's a whole heap of sort of syscall interfaces to dealing with signals that you don't really necessarily have to deal with. But the asynchronous library I've designed in a similar way, that you have callback functions, and callback functions are essentially the equivalent of interrupt handlers, that they'll get called asynchronously, meaning that when a signal comes in, they're called. So everything else sort of stops and it'll happen. And then they'll execute some sort of an interrupt routine that you can specify, such that when you get when you want to receive a packet, or you're getting a packet from this enemy in your project, your code will sort of interrupt itself, execute this code, and continue on. So this is sort of trying to emulate the functionality that you'd find in an embedded system. So now that's just a quick, very brief overview of what an interrupt is, and hopefully give some context to the library itself. And now I'm going to start looking at the library and how you use it. We'll start with some basics, and maybe at the end I'll do a couple of examples depending on how in depth I feel I need to go. For this example, I will be basically focusing on just the UDP, because this is what as I mentioned in my last video, this is what the project's going to be dependent on. And so the TCP being more complex, and also not finished because we don't really need it, I'll focus on just the UDP and how to use it and all of this thing for the project, which should hopefully help. So thank you, and I'll see you in the next video.